James Webb Space Telescope found a galaxy so old, so massive, and so completely wrong that when astronomers first saw it, they didn't believe their instruments. This is XMM-VID 1-2075. This isn't a galaxy that spins slowly. This isn't a galaxy that spins a little. This is a galaxy that for all practical purposes doesn't spin at all. And it existed less than 2 billion years after the Big Bang, when the universe was still a cosmic infant. That's not supposed to happen. That's not just unlikely. That's a contradiction. A galaxy behaving like an old, tired, burned-out relic from billions of years in the future. Found sitting right there in the distant, newborn universe, and completely, bafflingly still. Today we're going deep into one of the most extraordinary astronomical discoveries of recent years. What this galaxy is, why it matters, how we found it, and most importantly, what it might mean for everything we thought we knew about how galaxies are born, grow, and evolve. To understand why this galaxy is so shocking, we first need to understand how galaxies are supposed to form. After the Big Bang, the universe was a hot, dense soup of particles. It was uniform, almost perfectly smooth in every direction. But almost is the key word. There were tiny fluctuations in density. Some regions were ever so slightly denser than others. And over time, gravity did what gravity always does. It pulled matter toward those dense regions. Gas clouds began to collapse. As they collapsed, they didn't fall straight down toward the center. Instead, they swirled. But why? Because different parts of the collapsing cloud were being pulled slightly differently from slightly different directions. The result was angular momentum, a spin. Think of it like water draining out of a bathtub. The water doesn't just drop straight into the drain, it swirls. That swirl is angular momentum, and just like water in a drain, gas falling into a gravitational well tends to rotate. Over time, that rotating gas settled into a disk, flat and spinning, and within that disk, stars began to form. Those stars gathered into what we would eventually call a galaxy. So rotation is not just a coincidence in galaxies. Rotation is baked into the process of how galaxies form. It's a natural, almost inevitable consequence of the physics of collapse and angular momentum. Now, in the nearby universe, the universe as we see it today, in most large galaxies are spinning. Our Milky Way spins. The Andromeda Galaxy spins. Virtually every galaxy we look at rotates. But there is a small subset of the very largest, most massive galaxies, the true cosmic giants, that don't spin much at all. These are called slow rotators. Instead of stars orbiting the galaxy in one direction like cars on a highway, the stars inside slow rotators move in random directions, some going one way, some going another, creating what astronomers call dispersion-dominated kinematics. It's chaotic, it's random, it's like a swarm of bees, not a synchronized swimming team. These slow-rotating galaxies are fascinating, and they're also incredibly evolved. They're no longer making new stars. Their star-forming days are done. They're old, they're settled, and they've been through a lot of cosmic history. Current theories say that these galaxies became slow rotators through a long process, billions of years of mergers with other galaxies. When two galaxies collide and merge, their combined angular momenta can partially cancel out, especially if the collision isn't perfectly aligned. Do this enough times over billions of years, and you gradually remove the net rotation of the galaxy, leaving behind that chaotic, swarm-like stellar motion. The key phrase there is billions of years. The galaxy was initially selected by Dr. Ben Forrest and colleagues from this catalog because of its apparent brightness, its high photometric redshift, and its red spectral energy distribution, all of which are telltale signs that you might be looking at something very massive and very distant. But it was the magazine survey and the massive ancient galaxies at Z greater than 3 near-infrared survey that really put this galaxy on the map. Using the Keck Observatory perched on the summit of Mauna Kea in Hawaii, astronomers made an extraordinary confirmation. Previous magazine observations had confirmed this was one of the most massive galaxies in the early universe, with already several times as many stars as our Milky Way, and also confirmed that it was no longer forming new stars, making it what astronomers call a quiescent galaxy, a galaxy that has gone quiet. Our Milky Way has roughly 200 to 400 billion stars. And this galaxy, observed when the universe was barely 1.8 billion years old, already had several times more stars than that. It was already a finished, fully formed galactic giant. The Milky Way is still making new stars today, some 13 billion years later. But this galaxy had already stopped, done, retired, in cosmic toddlerhood. That alone was remarkable. But astronomers wanted to know more. Specifically, they wanted to know how the stars inside this ancient beast were moving. Were they rotating? Were they flying around randomly? And that's where the James Webb Space Telescope comes in. Researchers used James Webb's near-infrared integral field spectroscopy of this galaxy, a massive, quiescent galaxy at a redshift of Z equals 3.449. Redshift is how astronomers measure cosmic distance, and more specifically, cosmic time. Because light travels at a finite speed, when we look at distant objects, we're not seeing them as they are now. We're seeing them as they were when that light left them. At a redshift of Z equals 3.449, we're seeing this galaxy as it was about 12 billion years ago, when the entire universe was less than 2 billion years old. The light from this galaxy has been traveling through space for 12 billion years to reach us. And what James Webb found in that ancient light was staggering. James Webb Telescope used two of its most powerful instruments for this study: the near-infrared spectrograph and the near-infrared camera. Together, these tools allowed astronomers to not just take a picture of this galaxy, but to actually map how different parts of the galaxy were moving, essentially measuring the velocity of stars at different positions across the galaxy's face. This technique is called integral field spectroscopy. It's like taking thousands of tiny spectra simultaneously across the galaxy, giving you a detailed 2D map of stellar motion. It's extraordinary technology, and until JWST, this kind of measurement for a galaxy this distant was essentially impossible. The result was a detailed look at the kinematics, the motion of the stars inside this galaxy. And here's what they found. The galaxy has a stellar mass of about 330 billion solar masses. For context, our Sun is one solar mass. So this galaxy contains the equivalent mass of 330 billion suns, packed together, in a galaxy that exists when the universe is still in its infancy. The galaxy has a star formation rate of less than 1 solar mass per year, meaning it's forming barely any new stars at all. It's essentially a stellar graveyard. All those hundreds of billions of stars were formed rapidly in a burst of cosmic creation, and then, see, nothing. The astronomers also measured a large stellar velocity dispersion of approximately 379 kilometers per second. That means the stars inside this galaxy are moving, but they're moving randomly, like those bees we mentioned earlier. No ordered direction, no coordinated rotation, just chaotic high-speed motion in every direction. Now here is the number that really matters: the spin parameter of this galaxy. The galaxy displays a low stellar spin parameter, approximately 0.123, which is consistent with what astronomers call dispersion-dominated kinematics. In plain language, the galaxy is almost completely non-rotating. For comparison, a fast-rotating galaxy might have a spin parameter close to 1. The Milky Way, for example, is definitely a rotator. Its stars orbit the galactic center in a relatively orderly fashion. But this galaxy sits way down near zero. It is, by every measurable standard, a slow rotator. Let's be very clear about why this discovery is so scientifically disruptive. In the contemporary universe, most galaxies are supported by ordered rotation, but a substantial subset of the most massive and quiescent systems are dominated by random stellar motions and classified as slow rotators. These galaxies are widely thought to arise through processes that remove angular momentum and erase disk-like structures, but when and how this transformation occurs remains uncertain. That's the official, polished scientific language. In plainer terms, we kind of think we know how slow rotators form, through many mergers over billions of years, but we're not entirely sure, and this galaxy is throwing a serious wrench into our leading theories. Slow rotators are expected to be rare at early cosmic times, and observational studies of massive galaxies at high redshift have so far revealed only rapidly rotating systems. Every other massive galaxy from the early universe that we've been able to study shows clear rotation. But this galaxy is the exception, the anomaly, the galaxy that looked at all our models and said, no. This contradicts prevailing models that expect early galaxies to spin rapidly before gradually slowing over billions of years. Let me put this in perspective with a timeline. The universe is approximately 13.8 billion years old. This galaxy exists when the universe is less than 2 billion years old. For this galaxy to already be a slow rotator at that age, one of two things must be true. Either the galaxy went through an accelerated, incredibly rapid version of the slow merger process, packing billions of years of evolution into a cosmic blink, or it got there through a completely different mechanism that we haven't fully considered. And the models, frankly, struggle with both options. So how do you explain a galaxy like this? How do you get a massive, non-rotating, quiescent giant in the young universe? The leading hypothesis, and it's genuinely elegant, involves not a long history of many small mergers, but rather a single, spectacular, head-on collision. Here's the idea. Imagine two large galaxies, both spinning. Galaxy A is rotating clockwise. Galaxy B is rotating counterclockwise. They're moving toward each other, not on a glancing angle, but essentially head-on. When they collide and merge, what happens to their angular momenta? They cancel. Clockwise plus counterclockwise, if they're roughly equal in magnitude, equals 0, or very close to 0. The two rotations annihilate each other, and the resulting merged galaxy is left with barely any net spin. To explain this cosmic oddity, the researchers have an idea. Maybe XMM-VID 1-2. 075 didn't undergo countless mergers, unlikely in a universe less than 2 billion years old, but resulted instead from a single, spectacular collision between two galaxies that just happened to be spinning in nearly opposite directions. This is actually a far more efficient way to drain angular momentum from a galaxy than many small mergers. One perfectly arranged catastrophic smash-up could do in a few 100 million years what multiple mergers might take billions of years to accomplish. And here's the beautiful part, the evidence. Remember that faint, asymmetric glow we mentioned earlier? The excess brightness on one side of the galaxy? This galaxy shows an excess of light on one side, hinting at the presence of another object still interacting with this system and potentially scrambling its dynamics. For this particular galaxy, we see a large excess of light off to the side. That's suggestive of some other object which has come in and is interacting with the system and potentially changing its dynamics. That blob of extra light might be the remains of the other galaxy and the cosmic partner that slammed into this galaxy in an ancient head-on collision. A ghostly remnant still visible 12 billion years later in the light that finally reaches our telescope. It's like finding the crumpled remains of a car still embedded in a building. You weren't there for the crash, but you can read the whole story in the wreckage. Of course, this is a hypothesis, a very well-supported one, but still a hypothesis. The team is careful to say this is consistent with the data, not proven by it. Science is like that. You build the case piece by piece. So why does any of this matter? Why should you care about a galaxy with an unpronounceable alphanumeric name that exists 12 billion years away from us in time and space? Because of what it tells us about the universe's story. Our story. Every galaxy we study is a data point in humanity's attempt to understand how the cosmos went from a featureless, hot gas cloud just after the Big Bang to the extraordinary, structured, star-filled universe we inhabit today. Every galaxy that breaks the pattern forces us to refine our understanding. The existence of a massive, non-rotating galaxy like XMM-VID 1-2075 so soon after the Big Bang poses a significant challenge to existing galaxy formation models. These models generally predict that large galaxies should acquire angular momentum through gradual mergers and interactions over time. The presence of a slow rotator at such a high redshift implies that alternative processes, possibly involving early rapid mergers, could play a more significant role than previously thought. In other words, the universe might be more violent, more dramatic, more catastrophically eventful in its earliest years than we previously assumed. The calm, gradual story of galaxy growth might need to give way to a messier, more explosive narrative, one where enormous collisions shape cosmic fate in a single dramatic moment rather than a slow accumulation of smaller events. And this galaxy also raises another profound question. If this galaxy already stopped forming stars before the universe was even 2 billion years old, what stopped it? What mechanism shut off star formation in such a young, massive galaxy? Was it the merger itself? Was it a massive black hole at the center, blowing out the gas that would have formed new stars? We don't have complete answers yet. As scientists continue to analyze data from James Webb Telescope and other observatories, our models of the early universe will likely evolve, incorporating these surprising findings. And that's the thing about discoveries like this galaxies. They don't just answer questions. They generate better questions, sharper questions, questions we couldn't even have thought to ask before. It's worth pausing for a moment to appreciate the instrument that made all of this possible, because without the James Webb Space Telescope, this galaxy would just be a faint red smudge in a catalog. We would have known it was massive and old, but we would have had no idea it wasn't rotating. JWST observes in infrared light, wavelengths longer than what our eyes can see, longer than what Hubble was primarily designed for. This matters enormously for studying distant galaxies, because the expansion of the universe stretches light from distant sources. Ultraviolet and visible light from galaxies 12 billion light-years away gets stretched all the way into the infrared by the time it reaches us, a phenomenon called cosmological redshift. Hubble couldn't see this light effectively. JWST was built specifically to do so. JWST utilizes infrared technology to observe the faintest and most distant objects in the universe. Due to the redshift, a phenomenon where light from distant objects shifts to longer, redder wavelengths. As the universe expands, this galaxy is being observed as it appeared roughly 12 billion years ago, when the universe was still under 2 billion years old. And the specific capability used here, the integral field unit of NIRCam, allows JWST to simultaneously take spectra from thousands of points across a tiny patch of sky. For nearby galaxies, ground-based telescopes can do this. For galaxies this distant and this small in angular size, only JWST has the sensitivity and resolution to pull it off. We built a $10 billion telescope and launched it 1 million miles from Earth, and it showed us a galaxy that shouldn't exist. That's money well spent, if you ask me. Let's bring this home. This is a galaxy that formed when the universe was less than 2 billion years old. It grew to be several times more massive than our Milky Way. It stopped forming stars while the universe was still in its infancy. And somehow, against everything our models predicted, it barely rotates at all. It may have gotten this way through a single, catastrophic head-on collision with another galaxy of comparable size. A collision so perfectly tuned that the two galaxies' angular momenta canceled each other out, leaving behind a stillness that has now persisted for 12 billion years. Or there may be some other mechanism we haven't thought of yet. Something hiding in the early universe that we haven't found the language to describe. That's the honest truth of frontier science. We don't always know. We find the anomaly, we propose the explanation, we test it, we argue about it, we look deeper. And slowly, sometimes very slowly, we understand a little more about the universe we live in. This galaxy is one data point, one galaxy, one set of observations published in the journal Nature Astronomy by a team led by Dr. Ben Forrest at UC Davis. But that one data point is already challenging simulations, prompting theorists to revisit their models, and inspiring the next generation of observations. Maybe JWST will find more galaxies like this. Maybe they'll turn out to be rarer than 1 in a million. Maybe they'll turn out to be surprisingly common. Either answer will tell us something important. The universe is 13.8 billion years old. We've only been pointing telescopes at it for a few centuries. We've only had tools like JWST for a handful of years. The story of how everything came to be, how galaxies formed, how stars were born, how the universe went from a hot, featureless fireball to a cosmos rich enough to produce conscious creatures who wonder about it, that story is still being written. And every now and then, a galaxy like this reminds us just how much of that story we haven't read yet.